Imagine you're on the verge of a journey spanning billions of years, from the dawn of the universe to the cutting edge of modern knowledge. We begin at the singularity, the starting point of the first spark that ignited the Big Bang, the moment when matter, time, and space were born. This journey retraces how the universe formed and took shape from its mysterious beginnings. Next, we venture into the depths of our galaxy, the Milky Way, a cosmic city bustling with billions of stars and planets. Here, we'll uncover the secrets behind the evolution of the solar system and the origins of life on Earth. Then, we set out to discover the universe's most astounding phenomena, from gravitational waves rippling through the fabric of space-time to black holes that consume everything around them in a whirlpool of no return. These phenomena aren't just mysterious. They reveal new dimensions of the universe, challenging us to rethink the very nature of reality. As we draw closer, we stand at the threshold of dwarf planets and the distant worlds that surround us in the Kuiper Belt, icy and rocky regions that might hold clues about the stages of the solar system's development and the small celestial bodies orbiting its edges. Finally, we arrive in the era of modern technology, where exploration moves into the realm of colonization. With scientific advances that might make living on other planets a reality someday, humanity is reshaping its vision of the future and its place in this vast universe. Join us on this extraordinary journey, and don't forget to subscribe to the channel and like the video if you're eager for more cosmic adventures. So let's dive into the first chapter, how the universe began, from singularity to the Big Bang. Imagine this scene. Billions of years ago, the entire universe was condensed into a single point. A point of singularity, unimaginably dense and incredibly small. In this state, time and space didn't exist. There was nothing but a vast amount of energy compressed into an invisible space. Suddenly, without warning, the Big Bang occurred. But this wasn't just a chaotic release of energy. It was the dawn of an orderly cosmic system. From that very moment, all fundamental laws of physics emerged, marking the beginning of time and space as we know them. As Stephen Hawking famously put it, in A Brief History of Time, the Big Bang is the moment from which all subsequent cosmic phenomena sprang. But what happened after that monumental event? Quantum fluctuations began to lay the foundation for the universe we recognize today, setting it on a new course in its journey toward formation. Immediately following the Big Bang, scientists believe the universe underwent a rapid, explosive expansion known as cosmic inflation. In less than a fraction of a second, the universe expanded exponentially. A phase explained by physicist Alan Guth's theory of inflation, introduced in the early 1980s. But why did we need this theory? According to a recent article in Physical Review Letters, 2023, the theory of inflation helps explain the uniformity in temperature and density across the universe, despite the vast distances between its regions. Cosmic inflation, as some scientists argue, is the key to understanding the fundamental structure of the universe. This inflation triggered quantum fluctuations, which later became the seeds for the first clusters of matter. It's as if the universe was literally built from these tiny fluctuations, which existed briefly at atomic scales, only to expand and eventually form the galaxies we see today. On the other hand, this inflation left behind a unique signature known as the cosmic microwave background, CMB. This radiation, first discovered by Arno Penzias and Robert Wilson in 1964, earned them the Nobel Prize in Physics in 1978. Tools like the Planck satellite, launched by the European Space Agency in 2009, capture this first light of the universe, providing living evidence of the inflationary period. While inflation laid the groundwork, it was time for the next step: the formation of the universe's basic elements, a crucial phase in shaping the chemical composition of the cosmos as we know it. As the universe cooled over time following the inflationary period, nuclear forces began to bring together the first atomic nuclei, primarily hydrogen and helium, in a process known as Big Bang nucleosynthesis. According to research published in the Astrophysical Journal, 2022, the first few minutes after the Big Bang were critical for element formation, as temperatures reached billions of degrees, allowing atoms to fuse. In his book The Early Universe, physicist Edward Kolb notes that these elements laid the chemical foundation of the cosmos. Hydrogen, which makes up about 75% of the universe's matter, and helium, roughly 25%, became the building blocks for the first stars. These stars in turn acted as nuclear furnaces, producing additional elements. Why are these proportions important? They offer us a glimpse into the signature of the universe, allowing us to accurately determine its age. A recent study in Nature Astronomy, 2023, explained how scientists used these ratios to study the universe's evolution and estimate the time since its birth. But what if the universe we know is just part of a broader scene? This is where the concept of the cosmic horizon and theories about the multiverse come into play. As we advance in our understanding of the universe's structure, we encounter what is known as the cosmic horizon. The universe, within its physical limits, is confined to the information whose light has reached us since its origin. This restricts us to viewing an expanse estimated at 46 billion light-years. In his book Parallel Worlds, physicist Michio Kaku explores this concept, proposing the possibility of multiple universes beyond our field of vision. The multiverse is one of the most controversial scientific ideas and has gained momentum with developments in quantum mechanics. According to an article published in Science Advances, 2021, this hypothesis is not just science fiction, it's a logical outcome of the inflation theory. Could we be part of a repeating universe or infinite universes? This question drives scientists in fields like astrophysics to investigate the existence of other dimensions that may hold profound answers about the nature of our universe. Regardless of the universe's boundaries and mysteries, its current structure raises profound questions about how it formed and the influence of dark matter and dark energy, two enigmatic elements that constitute a significant part of this cosmic landscape. In the 1920s, Albert Einstein introduced his general theory of relativity, explaining gravity through the curvature of space-time. This led to the concept of the cosmological constant, representing a hidden energy that counters the gravitational pull of ordinary matter. Einstein's own book, Relativity, the Special and General Theory, details how general relativity established a framework for understanding the universe in ways that surpass Newtonian gravity. However, since the late 20th century, scientists have discovered dark matter and dark energy, two invisible components making up about 95% of the universe. Research published in Reviews of Modern Physics illustrates how dark matter helps bind galaxies together, while dark energy explains the accelerating expansion of the universe. But do we truly understand what this energy is? Scientists suggest that dark energy might hold the key to comprehending the ultimate fate of the cosmos, though their research is still in its early stages. This leaves a profound question. If the universe continues expanding due to dark energy, where will it eventually lead? With this question, we move on to exploring the grand structure of the universe, where familiar cosmic formations, like galaxies and quasars, begin to form and interact. The grand structure of the universe, galaxies and quasars. As the universe settled and hydrogen and helium formed, the first cosmic structures began to take shape. These early formations started as gas clouds, drawn together by gravity, eventually forming the first galaxies. It is believed that these galaxies arose from gravitational collapses of the cosmic gas, gradually accumulating until reaching a critical mass, which led to the formation of galaxy clusters. Galaxies were not alone. Exceptionally luminous objects known as quasars also appeared in the early stages of the universe. Quasars, the brightest celestial bodies, are the nuclei of galaxies containing supermassive black holes that consume vast amounts of gas and dust, generating enormous amounts of energy and radiation. According to a study published in Monthly Notices of the Royal Astronomical Society, 2022, quasars reveal the early stages of the universe, serving as time markers that help us trace its initial dynamics and evolution. Why are quasars significant? They provide time glimpses into the early universe, with light that has traveled billions of years to reach us, allowing us to study those ancient epochs. With a better understanding of these entities, we move on to explore the critical phenomena that continuously drive the expansion of the universe. In 1929, astronomer Edwin Hubble made a groundbreaking discovery known as Hubble's law, which revealed the expansion of the universe through the redshift phenomenon, where galaxies moving away from us exhibit light that shifts toward the red end of the spectrum. According to a study published in Astrophysical Journal Letters, 2023, Hubble's law demonstrated that the universe is not static but expanding, marking a turning point in astronomical science. Dark energy is another factor accelerating this expansion. The Hubble constant, which represents the rate of expansion, is measured with precision using advanced techniques, including space probes and ground-based telescopes. Research suggests that dark energy could cause the universe to expand indefinitely. But what drives this expansion? While we don't have a definitive answer yet, scientists believe dark energy may act as a repulsive force dominating the universe. This force raises questions about the ultimate fate of the cosmos. Will it continue expanding forever, or are there other possible scenarios? Advanced measurement tools may be our best hope in broadening our understanding of these profound questions. With advancements in science and the evolution of astronomical measurement tools, scientists are now able to measure distances and celestial bodies with greater accuracy. Cepheid variables, stars with regularly changing brightness, and supernovae serve as standard candles, reference points for measuring vast distances across the universe. In addition, scientists analyze the electromagnetic spectrum, which spans all wavelengths from radio waves to gamma rays, to observe celestial bodies. According to an article published in Scientific American, 2024, the use of the electromagnetic spectrum allows scientists to analyze the chemical composition and orbital speeds of celestial objects, enhancing our understanding of how these objects evolve and their positions within the cosmic fabric. How does the electromagnetic spectrum assist us? The electromagnetic spectrum provides fingerprints of the materials that make up these objects, enabling scientists to explore their chemical composition and formation history, thus deepening our understanding of the universe's nature. However, space-time itself remains an open frontier for research. Here, gravitational waves play a crucial role in helping us unlock further mysteries of this domain. One of the recent advancements in space science is the discovery of gravitational waves. First detected in 2015 by the LIGO Observatory, confirming a theory proposed by Einstein in 1915 as part of his general theory of relativity. Gravitational waves occur when massive celestial bodies interact, such as in the collision of black holes or the merger of neutron stars, producing ripples in the fabric of spacetime. According to a recent study published in Physical Review X, 2023, gravitational waves have become an effective means of observing cosmic events that cannot be seen through traditional telescopes. They serve as a background mirror for the universe, helping us uncover intricate details about massive objects and how they evolve. What does this mean for our future discoveries? Gravitational waves expand our understanding of how celestial bodies form and interact, potentially paving the way for a new comprehension of space-time and the universe as a whole. With all these advancements, it seems that exploring the cosmos is still in its early stages, leaving the future wide open for further discoveries. In conclusion, this grand journey of exploring the universe may have begun with the Big Bang. But it certainly doesn't end here. Every discovery leads us to greater and deeper mysteries. From the origins and formation of the universe to the enigmatic energy that governs its expansion to this day. It's an inspiring cosmic scene, and we are only at the beginning of understanding this boundless universe. If you are excited to discover more, don't forget to subscribe to the channel and activate the notification bell to receive all the latest updates. Also, if the video has added value for you, please hit the like button, as this greatly helps us continue to provide you with more engaging content. Get ready for the next video, where we will embark on a journey into the depths of our Milky Way galaxy. We will dive into its secrets, from stars and planets to its active centers and mesmerizing star clusters. Stay tuned, for the adventure in space has only just begun.